so let us look at this page. This is the second page. We have to go through a question here. This is the data obtained from experiments. So what they want us to do is constructing rate equations using concentration data. Okay, so let's see. Using following data from the experiments, construct a rate equation and calculate rate constant. That means count the K. Okay, so they have done 3 experiments. So the first experiment, the concentration of A is initially 0.04, B is this, and then initial rate. Initial rate is the R. Okay, so the R. So which means what? Which means we have R equal to K, A, concentration of M, which is unknown, concentration of B, which is also unknown. So initially, we don't know the value. So we put it in this way. Okay, now let's see more information here. Experiment 2. Experiment 2, 0.04, we keep the concentrations of A to be the same with experiment 1. And concentrations of B, we make it 1.5 times greater. Then the rate is 1.5 times greater. So from here, we can understand something. If you fix the concentrations of A, then the concentrations of B, which increase 1.5 times, the rate also increase 1.5 times. It shows that your B is of order 1. So first order. If you still remember just now on the first page, I mentioned that first order is where when the concentration is double, the rate is double. When the concentration is triple, then the rate is triple. So now, when you apply it accordingly, when the concentration is 1.5 times, then the rate is 1.5 times. They change in the same rate. 1.5 then 1.5. If they change in the same rate, that means it is first order. So the red color one show us first order. Okay, so N is first order. Now we look at the blue one. This round, we keep the concentrations of B. But we change the concentrations of A. So when the concentrations of A is 1.5 times greater, the rate is 1.5 times greater. So showing that the change is in the same rate, in the same ratio. Okay, so in that case, it is again first order. Okay, so first order. Then R equal to K, A to the power of 1, B to the power of 1. If let's say it is second order, how we see it? Okay, let's say I write away the first order because first order power 1 no need to write one. Okay, so we just write like that. That is the rate equation. Okay, let's come back to the question that I mentioned just now. If it is second order, how we see it? If this is 1.5 times increase in concentration, 1.5 square. 1.5 square is 2.25. Then your rate here must be 2.25 times greater. Okay, 2.25 times greater. So if that happens, then it is second order. If it's second order, so this is one of the way to determine it. Just look at it. Think about the concept of first order and concept of second order, and you can decide straight away. That is where we decide straight away. Now, how to calculate K? So of course, let me hold it first, because there is another way. Some people, they can't take it. They can't take I mean, they can't take the concept that I explained just now. Okay, so then there is another method. So this is what we call, okay, second method. So I will show you two methods. At the end, you just decide whichever method that stick to your brain, you just go ahead with that. Okay. Second method is like this. We use mathematics. We substitute everything to the equations. So experiment 1, the rate is 4.0 times 10 to the power of negative 4. Okay. Concentration of A is 0.040 to the power of n. Concentration of B 0.030 to the power of n. So experiment 2, concentrations of initial rate is 6.0 times 10 to the power of negative 4. K is unknown. A is 0.040 power m, 0.045 power n. Experiment 3, the rate is 9.0 times 10 to the power of negative 4. Okay, 0.060 power m, 0.045 power n. So we have equation 1, 2, and 3. So the second way to do it is we do simultaneous equation by elimination. So how to do elimination? We divide, so like 2 divided by 1. So if you do 2 divided by 1, left hand side you will have 6.0 times 10 negative 4 divided by 4.0 times 10 negative 4. So right hand side you have this. The thing is, although this is slower, but this method is very safe. So that's like this, and suitable for people who can't think of the order straight away. So then this method is suitable for you because we do calculation to get it. Okay, so 6 over 4 is 1.5. And then you can cut away the first bracket over there, the one with power m. And the one with power n, right? So basically what to do is you just leave the power n outside and you divide these two, So you divide that to 0.045 over 0.03, yeah? So you end up with 1.5 also. So because of that, you see left hand side is 1.5, so it's like 1.5 power 1. So this is 1.5 power n, so n is equal to 1. So that is how we decide. It's a safer way to decide. Not as fast as this one, but safer. So likewise, you can do 3 over 2. As you can see, we divide left hand side and right hand side. So this method is the mathematical method. Okay, so we can cut away this one. We can cut away the 10 to the power of 4. Okay, so we have 9 over 6. 9 over 6 is 1.5 again. So again, the power m, we leave it outside and we divide the 2 decimal over there. So 0.06 divided by 0.04, again we get 1.5, and hence m equal to 1.5. M equal to 1. Okay, so then we get R equal to K A power 1 B power 1. So this is the second method, longer but safer. Okay, so it depends on you. So you can decide on which method you like and you choose from there. Okay, now let's calculate the rate constant, the K, the small k. So to count the small k, right? So what to do is you can just substitute any experiment value into the rate equation. Let's say I use experiment 1. So the rate is 4.0 times 10 to the power of negative 4. The k is unknown. followed by concentrations of A, which is 0.040 power 1, 0.030 power 1. So we can get the concentration, we can get the values of K then by dividing. So we get K equal to 0.333. Okay, 0.333. So once we get the values of K, right, we have to determine the unit as well. So you know R, right? The unit is mole per dm cube per second. It's fixed one. The concentrations of A, concentrations of B. So altogether, this is concentration power 2. Power 2. Okay. Now, if you want to find the unit of K, right, imagine you divide them. This is the unit of rate divided by the concentration power 2. So at the end, if you simplify, mole over mole square, so you end up with mole negative 1. And dn minus 3 over dn minus 6, you end up with dn positive 3. And the per second remain. So that is how we decide the unit of K. So the unit of K is not fixed, it keeps changes. It depends on it is affected by the rate equations. Okay, so that is how we find the values of K. So like what I told you, this is the first method. We can find the order from, this should be the second method already. Just now the first method that I said is you find the order from the graph. The second method here is where we find the order from experimental value. We do something like this to find the order. Okay, so that means you can get order from the graph, you can get order from this table. So we know two ways to find the order already. There is one more way actually. One more way. So one more way to find order. So we need to know that also. So let's move on. 4.4. Calculating rate constants from half-life. Rate constant means K. So you can find K from half-life. If half-life is given, then you can find K. So, but this formula, right, is just for first order. Remember just now I mentioned first order has a constant half-life. So, and from there they work out the formula, and at the end they get this. K equal to 0.693 over half-life. So where you get the half-life, you get it from the graph. Then you put at the bottom here, divide by 0.693. And 0.693 is what value? Is actually ln 2. Ln 2 divided by half-life. Okay, so ln 2 is 0.693. So how they get it, we no need to really care about because it involves a lot of mathematical calculation. So we just take it and we just use it. So when should we use it? If they give you half-life, or maybe you can get half-life from the graph, then you can use this method to find K. It is fast. But it's just for first order. Second order, what formula? We are not going to care about that. It's not in syllabus. Zero order also, we don't care about that. So for zero order and second order, how we find K? We use this method. Okay, we use the methods written here. So just substitute theta to the equations and find K. So that's the method that we use. Now 4.5, you already know how to find K with different ways, from table or from this half-life formula. Now we are going to talk about the relationship of temperature and K. Okay, let's take a look here. increasing the temperature increases the values of K. This one we discussed before. So what I said is, if you increase the temperature, the rate is faster. When the rate is faster, then the rate constant K is greater. So that's why K equal to something like this. This is example, you know. It is not always first order for A, first order for B. Not always. For this case, yes. But for other case, maybe different. Okay, so this is example. We find K in that way. We divide the rate with the concentration of the reactants. Now, when temperature is increased, the kinetic energy of reacting molecules increases. So that means they move faster, resulting in more successful collisions. Logically true. If they move faster, then the success in their collisions happens more frequent. So reactants change faster to products, therefore concentration of reactants decreases. So they are trying to say that this one decrease very fast. Decrease fast when the concentration is higher. When temperature is higher. Not concentration. When temperature is higher, the concentration decreases quickly. The reactant decreases quickly because they use up quickly. If they decrease quickly, then the K will increase quickly. So this is mathematics, you know. So when the denominator decrease, then the outcomes is you get a greater answer. Okay, so using fractions, you see the next point. Using fraction above, numerator increases. Why numerator increase? Because rate, right? Rate increase. Higher temperature, higher rate. Rate increase. Okay, that is one thing. Rate increase at higher temperature. And denominator gets smaller. So as you can see the notes here, denominator gets smaller because the concentration of A and concentration of B, concentration of reactant decreases quickly because it uses up quickly at high temperature. So K increases. So there are two reasons why K increase, because rate increase, because concentration decrease. So of course, mathematically, it is very obvious K increase. So that is relationship between K and temperature. So we have done this. Now let's move on to the next part. So this is the third method that I'm going to mention just now. Okay, there are three methods to determine the order in the rate equation. The first method is graph. The second method is using the table, like just now. And now we come to the third method. We use reaction mechanism to determine the order. Okay, reaction mechanism. We can't use the overall chemical equation. Cannot. Overall chemical equation is on first page just now, the XY just now. So we can't use overall chemical equation to determine the order. But we can use mechanism to find the order. Let's see how. In reaction mechanism, right? If you remember your organic chemistry, we learn mechanisms. We learn mechanism, like for example the free radical substitution. We have three steps, like initializations, or the initial steps, and then the propagation steps, and then the termination steps. So we have three steps, So for example, so out of the three steps, right, one of the step is the slowest, and that step is called rate determining steps. Okay, so mechanisms have many steps, at least two steps. Okay, so one of the steps will be slower than the other one. The slowest one is known as rate determining steps. So rate determining steps is very important because they are slow. So if they are slow, right, the overall rate depends on this rate determining steps. Okay, so for example, when you cook, let's say for example, cooking take a lot of time. So because of that, you want cooking to finish quickly. So you have to be more. You have to pay more attention on cooking. Okay, you have to control everything quickly, control everything critically, so that the cooking process can go through quickly. Okay, so yeah, the slowest steps will affect the overall performance. Will affect the overall speed of the reactions. So this one is the rate determining step lah. So now let's see here. Okay, let's say one more example lah. Maybe it's not too clear. Okay, let's say you have your mechanism in this way. A to B is the overall reaction. But the mechanism, okay, so let's say I make it more complicated. XA plus YB become PC plus QD. So this is the overall reaction. So in this overall reaction, you can see there are two reactants and two products. So the rate equation is not affected by the X and the Y here because this is overall reaction. Now we look at the mechanism. So let's say mechanisms that we have a few here. Let's say we have A change to, let's say we have P amount of A change to, okay, the one P we have used P somehow. Okay, we have M amount of A change to P amount of C plus, let's say, okay, I simply create another thing, E. Let's say E, let's say PQ, okay, R amount of E. R amount of E react with Y amount of B. Let's say, to get, let's say, Q amount of D. Okay, now, okay, let's say, okay, let's say this is M, right? Okay, I purposely put like this, and okay, now, okay, I put X first so that my overall will be the same. I create this thing, so here I have to put X. Okay, so okay. Here I put X. So overall, overall equation is where you can cut the same thing on both sides, and then the remaining will add up on each side. So XA plus YB become PC plus QD. So the overall same with what I have on top there. Okay, now let's say the slow step is the first one. This is fast. Then the slow step is known as the rate determining steps. Rate determining step. So rate determining step is the one that can be used. Okay, I write down first. This is rate determining steps because this is slow. And remember that the rate determining steps can be used to work out the rate equation. The rate equation, you can see the rate determining step R equal to K. Okay, if your rate determining step has reactant A with X mole in front, then it's A to the power of X. A to the power of X. Your rate determining step has no B, that means B is not there. Or in other words, B is power or zero order. Okay, so your rate determining step can be used to work out the rate equation. You find out the rate determining steps, you look at the reactant, that reactant together with the mole will become the part of the rate equation. Okay, the reactant that is not there, then that means it's zero order. Okay, so that is how. This is the third way. Rate determining step determine the rate equation. Okay, now let's see more theory here. Okay, so in a multi-step reactions, so like here we have first step, second step. This is multi-step. The rate of reaction is dependent on the slowest steps. So this is the slowest step. The slowest step will affect the rate. Will affect the rate. Okay, so that needs the highest activation energy. So they are trying to tell you this one is slow because this one needs higher activation energy. This one is fast because this one needs lower activation energy. Okay, so that means this one affect the rate a lot. Okay, so why this affect the rate a lot? Because the second step is waiting for E to form. If E is formed, then E can quickly change to the product. But E forms slowly because this is slow. E forms slowly, so the B is waiting for the E that's formed slowly, to form the product. So that's why this is rate determining steps. Okay, once this happens, then this one can quickly form product, so it doesn't affect anything. But the first steps affect. Okay. Now, next point, rate equation includes only reactants that are present in the rate determining steps. This is what I mentioned. This is rate determining steps. The reactant here, together with the mole in front, will form the rate equation. Okay, will form the rate equation. So rate equal to K, concentration of A to the power of X. So the power X refer to rate determining step, not refer to this one, the overall. Don't expect the overall X here is always happens here. Is sometimes no. Sometimes here overall is 3, but here is maybe 1. Okay, so you have to use the 1 instead of the 3 in your rate equation. So follow the rate determining step, in other words. So I will give you more example later on other page. So let's move on first. The order with respect to the reactants are the moles of the reactants in the rate determining steps. So if the rate determining step take X mole, then the order here is X. And if reactant B is not in rate determining step, that means reactant B takes order 0. Order 0. Okay, so yeah, like that.